let's move forward and take an example for homogeneous catalysis. Let's take an example between sulfur dioxide and O2 in presence of nitrogen oxide. All of them are present in gaseous state G, and this is also G. Many of you may know it produces SO3. Now let's balance it. It is 2 here, 2 to 4, 6, and no, let's put 2 here and 2 here. Now see, basically let's try to discuss the mechanism for this homogeneous catalysis. We are discussing mechanism for this. What happens in this? See, all the reactants as well as catalyst are present in same phase, then it's known as homogeneous catalysis. See, first the reactant, any of the reactant, either A or B, let's present this A or B, this try to react with this catalyst, and they form an intermediate compound, basically less amount of energy is needed to form this intermediate compound, and this is very unstable. It tries to, this intermediate, IC stands for intermediate compound, reacts with, for example this is A, now it reacts with reactant B and forms the final product, and we get our catalyst back. This is the basic mechanism. Basically it is the intermediate, I stands for intermediate, C compound formation, F, T theory, IFCT, intermediate compound formation theory. This governs this homogeneous catalysis. Now let us look at our example. This, it is SO2 plus O2 in presence of nitrogen oxide. These are all in gas phase. 2 here gives 2 times SO3. Now first this oxygen tries to react with this nitrogen oxide, monoxide, NO plus O2. This gives NO2. It's also gas, and this NO2, nitrogen dioxide, reacts with this SO2, sulfur dioxide. Now nitrogen dioxide plus sulfur dioxide gives our sulfur trioxide, plus we get our catalyst back, NO. I hope it is sufficient. Now we discuss the heterogeneous catalysis. I hope you remember, in this type of catalysis the reactants and catalyst are not present in same phase, For example, let's take an example, Haber's process. Haber's process, you may have heard. It's the process in which we produce ammonia. Basically these two are gases, and this reaction takes place in presence of iron. Iron is solid, and we get our NH3. See, this is gas, and this catalyst, it is in solid state, so this will fall in heterogeneous catalysis category. Now, mechanism for this heterogeneous catalysis, basically it is governed by two theories. First is activated complex theory. Activated complex theory, and second one is our adsorption theory. Adsorption theory. Now let us discuss this first. See, basically, let's make a new slide. See, consider this as our catalyst surface. It should have free valencies. Catalyst should have some free valencies, because only that it can absorb these are the free valencies. These are free valencies. Now it's our A plus B. First, what happens? This A and B try to form a complex with this catalyst. This is our catalyst, and they form an activated complex like this. See, it's A here, and here this is our catalyst surface, here it is B. Now, as you know, catalyst is an exothermic process. That means heat is evolved. Actually, this heat which is evolved here increases the activity of the catalyst also. Now after this A and B will try to form a bond between them. Actually, they will try to react on this catalyst surface like this. Now A and B will try to form bond, and after this A and B, the next stage will be when A B, this will be removed, and we will get our catalyst back like this. And second theory which governs this is adsorption theory. Basically, what adsorption theory tells us, see, first the reactants adsorb to this surface. First reactants adsorb to the catalyst surface, to catalyst surface. Then there is a type of chemical bond or reaction between, there is a reaction between the reactants, and at last these products, when reactants react, they will form products. These products will dissolve from the catalyst surface, and we'll get new space for new reactants over there. This is all for these two types of catalysis.